I sent out an email yesterday about the SciFinder, directions for using SciFinder. We no longer have a Reaxis database. We now have the SciFinder database, which is from the American Chemical Society. This is for searching the literature using structures. So you draw the structure and then you can search and get the literature references. And this is required in your group report. This week in lab we'll be doing mass specs as the product. Each group will do a mass spec, GC mass spec. And then after that we'll have lab lecture during lab downstairs. Mass spec, any questions about the what's going on when we do a mass spec? The instrumentation, process, any questions about that? Go, Mena.
What was the standard value for alcohol? Was it 29?
Uh-huh.
Or was it 30? It's 29.
Well, if it's CH3, CH2, that would be 29. 2 carbons and 5 H's is 29. We looked at a couple of examples, alkanes, tertiary carbocation. We looked at isotopes for bromine and chlorine, isotope patterns there. And we're ready to look at the next page. We're going to look at different functional groups. This here being an ether. And here's a mass spec. Okay, you ready? This ether has a molecular weight of 74. That's molecular weight, right? C4H10O, 74. That's a whole number. By the way, we're typically doing whole numbers in the mass spec that we're doing. You can do what's called high-res mass spec. The textbook talks about that. That's where you get like 3 or 4 decimal places. Here, typically whole numbers. Or low-res mass spec. Okay, molecular weight of 74. Do we have a molecular ion? Looks like we do. Right here at 74. So this would be the M+. Usually just stated M+, of course the molecular ion is actually a radical cation, so it's actually a radical. Sometimes that little feature is left off, just saying M+. 74. So that's where the original molecule was ionized by some method, such as electron impact. Then it was pulled through the magnet deflected it at a degree that equaled, after calibration, 74. Because you can turn it degree of deflectance into molecular weight. Because the deflectance is based on the molecular weight. Sometimes a physics law. It involves calibration. It's very turned into a simple idea. But the original molecule can also fragment as it moves through the process. And anything else you get would be a fragmentation. We got a big peak here at 59. It's obviously not 74, so this molecule has lost something. How much has it lost? How much has it lost here? 15? So it's M minus 15. Understanding how much is lost is important because you know what was lost. So the original has lost 15. What's 15 sound like? Methyl. Methyl, standard methyl. A carbon and 3 H's. How could this thing lose a methyl? Well, it's got this methyl hanging on the end here. Maybe it just cleaved right here. If it cleaved there, keep it in mind the original was a radical cation. Radical cation, when that cleaves, what do you get? You get a cation plus what? Plus a radical. The cation equals 59 because there's a peak at 59. Well, if you add this up, this is 59. Plus what else is formed here? The CH3. What's that species going to be? A radical, because a radical cation cleaves to give a radical and a cation. We'll just keep it as simple as that. We're not going to look at mechanism for how it cleaved. The textbook may actually do that. We're not actually going to move arrows and show the mechanism for the cleavage. But that's not the base peak. What's the value for the base peak? 31. What is that? M minus what? 43. What's 43 typical? Typical of anything. Methyl's 15, ethyl's 29. What would a propyl be? CH3, CH2, CH2. That would be 12 times 3 is what? 36? 2, 4 is 7. Huh. What do we get? What's a propyl? 43. It's like it lost 43. Huh. Hold on now. How could that molecule lose a propyl? That molecule doesn't even have 3 carbons bonded together sequentially. Are we getting this right? Is 74 minus 31 43? 74. Was this 43? 1, 2, 3. 12 times 3 is 36. 2, 4, 7. That's 43. Yeah. Not sure what that could be. I mean, you can envision that molecule losing 3 carbons and 7 H's, but it would have to be sort of a double fragmentation. This is actually not easy to predict. I don't remember that being that case. Not easy to predict. Let's look at another peak. Hold on, before we go any further, let's look back over here. Why did this cleave here to give this cation? This is a very common cleavage that we're going to call alpha cleavage. What is alpha cleavage? Here's what alpha cleavage is. It's where you cleave to give a cation next to a lone pair or a pi bond. Where did we put the cation at with this cleave? Next to a lone pair. Why did we put it next to a lone pair? Why would this cation want to form? It looks like it's a primary carbocation. Does it have any more stability than being a primary carbocation? Starts with an R. We cleave to give a resonance stabilized cation. So this is a very predictable cleavage site. Loss of 15 would be very predictable here. Why is it called alpha cleavage? Because from some group, either the heteroatom or maybe a carbonyl, the first carbon from that is called alpha. The next carbon is called beta. In alpha cleavage, you cleave between the alpha and beta carbon. But the more important thing to remember is you cleave to give a cation where? Next to a lone pair or next to a pi bond, which we'll see later. Let's not look at anything else here because the base peak is really not that. I don't know what the structure of the base peak is. This is your very predictable cleavage. What is this right here at 75? There's a little peak there. What is that? M plus 1, yeah, that's M plus 1. What is the M plus 1 peak? What is the structure of the M plus 1 peak? With the chlorine and bromine, we had an M plus 2. What was that from? Major isotopes. Do we have any isotopes that are here that could give us +1? Yes, carbon. 99% of your carbons are carbon-12, but 1% are what? Carbon-13. C4H10O. If you add that up, you would go 12 times 4 is 48 for carbon, right? That's assuming all carbons are 12. Is there a chance that one of those carbons may be a carbon-13? Yes, there's a very slim chance, because 1% of the carbons in your body are carbon-13s. 1% of the carbons in the air is carbon dioxide or carbon-13s. 1% of the carbons in, there's a chance that one of these carbons may be C13. Then we would have 12 times 3 is 36. Then we would have a 13, and that would be 49. You would get one more than 48. If you added it all up, you would get one more than 74. This is where you have one of the carbons in your molecule is C13. That's possible, yeah? Is it not? Possible, right, Andy? Is it possible to have two carbon-13s in this molecule? It's possible, but that's going to be even less likely. Well, maybe it just didn't show up and it's in the noise there, but it gets. What's the likelihood of all four of these carbons being C13 in a natural sample? Not that likely. But having one is fairly likely. At least a very small, like 1% chance. So that's a C13 isotope. Let's look down below. Here's a amine, a primary amine. Well, this is a nice clean mass spec. It looks like one predominant cleavage peak. Molecular weight is 101. Molecular ion is absent, or it's very minor. It looks like there's a little something, maybe, but it's pretty much absent, yeah? First thing we can say about this is the molecular weight is odd. All previous examples of the molecular weight was even. Unless you consider it an isotope of carbon. But typically with carbon-12, it's always going to be even the previous ones. Why is this one odd? Molecular weight is odd because the compound has an odd number of nitrogens. This is just a little kind of tricky thing to be aware of. If a compound has an odd number of nitrogens, the molecular weight will be odd. For example, ammonia has one nitrogen. Molecular weight is odd. What's the molecular weight? 17? Odd. But if we have hydrazine, which is NH2NH2, or N2H4, what's the molecular weight of this? 32. Odd number of nitrogens, odd molecular weight. Even number of nitrogens, even molecular weight. With 0 being an even. If it has no nitrogens, it'll be even. No nitrogens, that's why it was even up here. That's called the nitrogen rule. That's called nitrogen's trivalent. There may be other atoms that follow that rule, but for the main ones for us, nitrogen, odd number of nitrogens, odd molecular weight. I mean, you can use that, say, what if you're isolating some new cancer-curing agent from seaweed that grows off the southeastern tip of India, in the ocean, Indian Ocean. And you isolate a drug that cures cancer. And you run the mass spec and the molecular weight is 766. What does that tell you about the number of nitrogens in the molecule? Even number of nitrogens. Or none. All right, there's big information. Helps you figure out the structure. Okay. What type of cleavage do we expect here? Starts with an alpha. Where do you want to cleave here? You want to put cation where?
Next to a lone pair.
Next to a lone pair. Atom next to a lone pair. Do we want to cleave here?
No.
If we cleave there, we would maybe put cation here and radical there. Well, hold on. We want to cleave with a cation. We can't cleave here because the lone pair needs to be next to the cation. We need to cleave here. If we cleave there, we would get that fragment and that there with the cation where? Carbon next to the lone pair. What would this fragment be? That would be a radical. Cleavage to give a cation next to a lone pair. Why? Because this would be resonance stabilized. And we would get that resonance structure, which is a major resonance structure, more bonds. What is the mass of this? This is M minus what? What did we lose? We lost a tert butyl. That's basically a butyl. That's C4. What's the formula of this? C4, 333H9. 12 times 4 is 48. 48 plus 9 is 57. This should be 101 minus 57 equals what? Is it 44? I'm hoping that that big peak is at 44. Is it? By the way, you already knew what we were doing because I had it drawn there, right? 44, yeah? What is that? That's this, M minus 57. M minus T butyl. Very predictable cleavage because it's resonance stabilized. Where do you cleave to make cations? Next to lone pairs and next to pi bonds. We'll do pi bond in a minute. We can maybe see other stuff. What is this here? This is 81, 2, 3, 4, 5, 86. Is that anything we can predict? 101 to 86, that's loss of what? 15. What did the molecule lose to form 86? Methyl. Show the 86. What's the structure of 86? Most likely structure of 86. Is it going to just lose any old methyl, or is it going to leave a methyl to give the best cation upon losing methyl? Show the peak at 86. It's not a favorable cleavage compared to the 44. Actually, I was thinking of something else. It actually is, it's actually another alpha cleavage. I actually see two that could have been proposed. If we cleave here, what do we get? I'll draw it over here. We get that cation plus what? It's the CH3 radical. And the mass of this would be 86, yeah? That's another example of alpha cleavage. Very often you can do two alpha cleavages. You can cleave here or here and give this resonance stabilized cation or give this resonance stabilized cation. I won't draw the resonance structure, but here. Well, let's look at this. Both of these cations are resonance stabilized. Both would be predicted. Well, why is 44 so much more favored than 86? Why is this pathway more favorable than this pathway. It's not because of the resonance stabilized cation. It's actually because of the other fragment, or radical. Which radical is more stable? That one or this one? Why this one not?
Tertiary.
Why is a tertiary radical more stable than a methyl radical?
Because of more lone pairs.
Well, there's no lone pairs here. Starts with an I. More induction, but why does induction make a radical more stable? We can keep going on and on. Induction, there's more induction here. But does induction stabilize a radical or destabilize it? What is a radical? Is it electron rich or electron poor? Why do you say electron poor? Why? If you were in law school, you wouldn't get far with that argument. Gotta have a good argument. Why is a radical electron poor? Does that carbon have an octet? How many electrons does that carbon own? 7. It does not have an octet. It needs one more to have an octet. That's why it's electron poor. It doesn't have an octet. You stabilize cations, radicals, just like carbocations. Electron donating groups stabilize radicals. A tertiary radical is more stable than a methyl radical, just like a tertiary cation is more stable than a methyl cation. It cleaved this way, not because of so much of the cation, but because the radical was more stable. Now the radical doesn't show up, but its formation is still favored compared to formation of that radical. So that's probably why this is more predominant cleavage pathway. Allison, you had a question?
Oh, yes. Why did you cut off that specific carbon versus any of the other ones?
Well, cleaving there gave a resonance stabilized cation.
Oh, okay.
So we did alpha cleavage. But we could have maybe cleaved here. Would that have been reasonable? If we had cleaved there, we could maybe propose that cation, which would also be 86. Wouldn't that also be 86? What can you talk about the stability of that cation? It's not resonance stabilized, but it is what? It is tertiary. But typically resonance is better, even if it's not tertiary. But, like I said, there could have been another way to cleave a methyl. That would have been a reasonable proposal. Typically, though, we want to do alpha cleavage. Make cations next to what? Lone pairs of pi bonds. This is not too bad. Okay, anything else on that one? By the way, odd number of nitrogens. Molecular ion is odd, but cations are even. Notice the cations are even. In the previous examples, molecular weight was even, and your cations were odd. So both of those flip when you have an odd number of nitrogens. Okay, here is a benzene compound with a propyl side chain called propylbenzene. Molecular weight is 120. Again, when you add the molecular weight up, it's carbon's 12, H is 1, oxygen 16, nitrogen 14, just even or whole numbers. If you want to do an isotope, then you use the different whole number. 120, do we have a molecular ion? Yes, right here. 121, what is that? It's for one of the carbons of the molecule is
Carbon 13.
C13. When you do mass spec, you see individual molecules. You don't see averages. The molecule will either have, how many carbons we got here? 6, 7, 9? We'll have 9 carbons with all being 12, or you may have molecules with 8 that are 12 and 1 that is 13. They're actually, both molecules are actually both hitting the detector, but you're just getting one scan, one read. This is 2 different molecules. One molecule can't give both molecular ions. It's 2 different molecules being present. One of them having 1C13. If this thing cleaves, where do we want to put cation? Next to what? Next to lone pair of pi bonds. So why don't we cleave right here? If we cleave right there, we could say cation there plus what? What would be the other fragment? Ethyl radical. So that means this would be M minus what? What did we lose? 29. 120 minus 29 would be 91. Do we have a peak at 91 for that? Yes, right there. 91. Why do we put cation next to pi bond? Because now we can do windshield wiper. That bond is not kind of fully there. But if it was here, we could just boop, move it out, put cation here. Move it out. And we end up with, now we're doing resonance around the benzene ring. These electrons just windshield wipered out, leaving plus here. And we can do additional resonance structures. Move these over, put plus here. Move these down, put plus there. You should be able to draw them all. This is a resonance stabilized. This type of cation that's stabilized by the benzene ring is called a benzylic cation. A carbon coming off a benzene ring like that, typically sp3, that's called a benzylic carbon, or the benzylic position. We'll hear that term later, including organic too. Benzylic cations are resonance stabilized. They're going to be very favorable to form. The basic one with just the benzene ring and the CH2 there is 91. You very often see 91 in a mass spec, being just a simple benzylic cation. Don't tell anybody that this thing is known to rearrange, but I'm not going to show you that because it's really not needed at this point. Maybe sometimes you will hear talk about the rearrangement of the benzylic cation. Pretty major cleavage. Everything else was sort of minor. I mean, we could have cleaved here. If we'd cleaved there, call that A, this B, this A. If we'd cleaved at B, we would have gotten what? That's generic for a benzene ring. Isn't that like Greek for phi? Something like that? Yeah, it's just generic for a ring, so I don't have to take time and do this and do this. Okay? That's just generic for a ring, and we get boom, boom. We have a cation there plus what? What's a CH3 radical? This is not a great cleavage because that's not resonance stabilized. There's no p orbital here. That's an isolated cation. Theoretically possible. If it did, it would be M minus 15. Do we have an M minus 15? 120 minus 15, 105. Right there. It'd be 105. I mean, that's possible. But that's not a cleavage that we would predict to be very prevalent. The 91 peak, which is resonance stabilized, would be more prevalent, and the one that we would pick and base answers on and say, we got to have 91. Compound below is actually an isomer of the one above. It's also 120. M plus 120. But the base peak down here is 105. Why is 105 the base peak down here? Show the structure of 105. Never mind. Here it is, right here. I see some students want to cleave right here and say, boom, I can cleave them up and get 105. Well, you're not cleaving in the right place because you're not going to resonance stabilized cation. Cleavage here will give that plus the CH3 radical, and that's 105. Cleavage here would give what? Would give that cation plus the CH3 radical. That cation is not resonance stabilized. You need to think about that. That is not resonance stabilized. You cannot draw any resonance structures of those, of that. That is not resonance stabilized. If you think about structure, orbitals, it is not. Resonance stabilized would be the, what do you want to call this cation that's next to the benzene ring? Oh. Benzylic cation would be resonance stabilized. So, what we have on this page is two isomers. They both have mass of 120, but they have very different mass specs. Up here, you expect loss of what to give a benzylic cation? 29. But down here, you expect loss of what? 15. And if you understand that, you see the mass specs are very different. And you can... Would these compounds be that different on IR? No. You would not be able to tell them apart on IR. They both have sp2CH, they both have sp3CH, they both have aromatic. IRs would be indistinguishable. Mass spec, though, clearly distinguishable if you know basic cleavage patterns. Everybody see that? Okay, let's move to carbonyl compounds. Is molecular weight odd or even? Even, there's no nitrogens. It's 86. And there's an 86 right there. Okay, if this radical cation, which is formed in the first part of the mass spec, if it then cleaves, it will give a radical and a cation. Well, what type of cation are we going to show? Where do you want to make cation in? Next to what?
That's the one.
Yeah. Now you have a pi bond and a lone pair here. With carbonyls, it's the lone pair that we're looking at. I mean, next to the lone pair. Which carbon is next to a lone pair? Tell me when I show the carbon that's next to a lone pair. Is that one next to a lone pair?
No.
That one?
No.
That one?
Yes.
There's no lone pair next over there. I'm talking right next door. Is there a lone pair next to this carbon?
No.
How about that one?
Yeah. Yes.
Yes. That carbon has lone pairs next door. So where do you want to put cation at? There?
No. 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 Yes.
Yeah. It may look funny because it's double bonded, but Where do you put cations? Next to lone pairs or, okay? We want to put cation there. How do you get cation there? Do you cleave here? No. We want to cleave here or there. We'll cleave both places. This is going to be A. If we cleave A, we're going to get, well, it's already drawn. What do we get if we cleave A? We're going to get this cation. We're going to cleave it, and we're going to say we're going to put cation over here on the right, which would be this, plus what? And propyl radical. And this would be M minus what? What's a propyl? 43. 86 minus 43 is what? Actually 40, no, 43? Is that 43? Yes. It's for that cation. That's actually the base peak. Why is this cation